Imagine you put a pair of gloves in two boxes and ship one to Tokyo and one to New York. The moment you open the New York box and see a left glove, you instantly know the Tokyo box holds the right glove. No mystery, no magic. The gloves were always left and right. You just didn't know which was which until you looked. Einstein believed quantum mechanics worked exactly like this. Two entangled particles, like two gloves, each had a definite hidden state before you measured them. The weirdness was in our ignorance, not in reality. He was wrong. And in 1964, a physicist named John Bell proved exactly how wrong, by discovering a mathematical test that separates gloves in boxes from genuine quantum strangeness. Then experiments ran the test, reality failed it. Here is what quantum mechanics claims: two particles can be entangled, their fates linked at the moment of creation. But before measurement, neither particle has a definite spin. It's not that the spin is hidden, it's that it genuinely doesn't exist yet. The act of measuring creates the outcome. Separate the particles by any distance, a meter, a kilometer, a light year, then measure them simultaneously. They will always show correlated results. If one spins up, the other spins down, instantaneously, regardless of distance. Einstein found this intolerable. Nothing travels faster than light. If measuring one particle instantly affects another particle a light year away, something has broken causality. His explanation: the particles carry hidden instructions, a predetermined table of responses to all possible measurements. They look random only because we can't see the instructions. This was called the hidden variable hypothesis. It was a perfectly reasonable scientific proposal, and Bell found a way to test it. Bell's insight was this: if particles carry hidden variables, if they have definite answers to all possible measurement questions, then their correlations cannot exceed a certain mathematical limit. This limit is called Bell's inequality. Think of it as a test for pre-existing definite values. If you measure particles along three different angles, and the correlations between measurements stay within a certain bound, then hidden variables could explain the results. If the correlations exceed that bound, if the particles are more correlated than any hidden variable theory allows, then no predetermined instruction set can explain what you're seeing. The particles would have to be, in some sense, genuinely connected across space, not like gloves, where the information was always there. Something fundamentally different. Quantum mechanics predicts that entangled particles will violate Bell's inequality. The correlations will be too strong, too perfectly coordinated, impossible to explain with pre-existing hidden states. Bell had drawn the battle lines. Now someone had to run the experiment. In 1982, physicist Alain Aspect ran the first definitive test in Paris. The results were unambiguous. Entangled photons violated Bell's inequality exactly as quantum mechanics predicted. The correlations were too strong for any hidden variable theory to explain. The experiment has been run dozens of times since, each time closing possible loopholes. In 2015, 3 independent labs simultaneously published loophole-free Bell tests. In 2022, Aspect, Clauser, and Zeilinger received the Nobel Prize in Physics for their work. The verdict is final. Hidden variables are ruled out. Einstein's gloves in boxes picture of reality is wrong. So what replaces it? This is where physics reaches its horizon. Bell's theorem eliminates one kind of explanation: local hidden variables. But it doesn't tell us what the correct explanation is. Physicists have been arguing about this for 60 years. And the debate is still open. Some accept non-locality. Particles are genuinely connected across space, though this connection can't be used to send signals faster than light. The universe has a kind of invisible glue binding distant things together. Others accept the many worlds interpretation. Every measurement causes reality to branch. The particle spins up in one branch of the universe and down in another. Both outcomes happen. There's no collapse, just proliferation. Others accept fundamental randomness. Some outcomes simply have no cause. They just happen. The universe contains irreducible dice. Each interpretation preserves the predictions of quantum mechanics. None can be ruled out by experiment. Bell's theorem didn't reveal what reality is. It revealed what reality cannot be. There is a pattern here. Wigner showed that mathematics cannot explain its own effectiveness. Gödel showed that logic cannot prove its own consistency. Turing showed that computation cannot answer its own boundary questions. Chalmers showed that science cannot explain its own observers. The arrow of time showed that physics cannot derive its own temporal direction. And now Bell shows that physics cannot tell us what reality is made of at the deepest level. The tools work. The predictions are perfect. But the nature of the thing doing the predicting remains out of reach. This is not a failure of physics. It is a discovery by physics that certain questions are not merely unanswered but unanswerable from inside the framework. The horizon is part of the structure. The next time you flip a coin, consider this. According to quantum mechanics, there may be physical events at the subatomic level with no cause whatsoever. Not unknown causes. Not hidden causes. No cause. Just an outcome. Chosen by nothing. Bell proved we cannot escape this conclusion by hiding behind ignorance. The choice between quantum interpretations is a choice about which part of your picture of reality you're willing to surrender. Einstein couldn't make that choice. Most physicists today have learned to live with the question instead. Some questions don't get answers. They get sharper.